Okay, so last time we began looking at how to actually solve the wave equation, right? Remember, we spent about a little more than half of one of the lectures last week explaining where the wave equation comes from and actually deriving it from some basic physical principles. And then last time we began looking at how to find a solution. And so on the screen, you see written a quick summary of what we arrived at the end of the last lecture. And so remember that the wave equation is a second order equation which relates two time derivatives to some two spatial derivatives, and in particular the second derivative with respect to time of u is equal to some number c squared times the second derivative with respect to x. And in this case, remember physically the function u measures like if you consider, for example, a string which is directed along the x-axis that is oscillating, the function u measures the displacement of the string from the axis at a certain point. And we saw that such a function will be a solution to this equation under certain physical assumptions. Right, and so we're, in this case, or last time we focused on last time and this lecture, we're going to focus on the case where the input x is just the whole real line. So you can imagine the string is infinite, but maybe there's not much going on after a certain point. If you want to understand what happens for like a finite interval or a finite piece of string, it turns out that in order to solve this equation explicitly, you have to do a little bit more work, but we'll talk about that more later on in the semester. So for now, we're just looking at what turns out to be the easiest case, which is where the domain is the whole real line. And so based on the analysis we did last time, we have a candidate for or not a candidate for, we have an actual solution formula where I can write my function u, we saw, as a sum of two functions, f and g, which are both functions who have a single real number as their input, but f is evaluated at x minus ct, and g is evaluated at x plus ct. And the interpretation of this is that, well, you can imagine, think about the graphs of the function f and the function g. As time evolves, what's going on when I look at f of x minus ct, this moves, in time the graph moves to the right at speed c. On the other hand, for the function g, as time evolves, the graph of g moves to the left at speed c. And we looked at an example of this previously. And so you can think of f and g as describing certain waves. And so the general solution formula shows that the wave equation or solutions to the wave equation are always given by a sum of two different waves which are moving in different directions. Or another way to say this is it's a superposition of these two waves, which one is moving to the left and one is moving to the right at speed c. But when you add them together, right, maybe it doesn't appear that that's what's happening, because the functions can interact in complicated ways when you sum them together. Right, and so in order to actually arrive at a more explicit solution that's not just in this abstract form with the function f and the function g, we have to impose certain initial conditions. And so the next thing we turned to was the initial value problem, which says that, okay, if you take a solution to the wave equation and you also impose an initial position, say when time is equal to 0, u is equal to this function phi, and an initial velocity, for example, when t is equal to 0, the velocity or the time derivative of u is equal to this function c, psi, then it turns out that, right, so this is called an initial value problem, and under these conditions, it turns out that you can find a more explicit solution to the wave equation defined in terms of the initial conditions, which is something you can actually calculate. And so the formula that we mentioned and looked at an example for is something that was originally shown by a mathematician named D'Alembert, and so it's usually called D'Alembert's formula. And so I've written this as a theorem below, where, okay, what is the solution? I have a certain term involving phi, and then a certain term involving the integral of c. And the inputs and the boundaries for the integral depend on x minus ct and x plus ct, respectively. Right, so you can see if you, for example, break up this integral, you can write, you can see the connection with the more abstract formula for u that we initially derived. Right, so that was just some quick review of where we ended up at the last lecture. And so what we're going to do today first is actually prove that this formula is valid, and in particular explain in the argument you'll see how one would actually find this formula, right? Of course, if I give you this formula, you can just check that it works. It's a little bit more interesting to also derive it from the basic information that's given to us above to explain how anyone would have been able to come up with this. Both of these things are important. Right, and so what we're going to do is, well, we have this formula, right? So we know that u of xt is equal to f of x minus ct plus g of x plus ct, right? And so this is what we showed last time. And so what we're going to do is try to relate this to the initial conditions in some way. In particular, notice that if I set t equals 0, then my first initial condition tells me that that has to equal phi of x, right? So when I set t equals 0, what happens if I set t equals 0 on the right-hand side? Well, I just get f of x plus g of x, right? And so this immediately tells me that whatever these functions f and g are, when I sum them together, I have to get phi, which is given to me as an initial condition. Okay, and so let's try to do something similar for the initial velocity c. This is a little bit more tricky because I don't have just u evaluated at some point is equal to c. I have something involving instead the derivative of u. And so, well, what does this initial velocity condition actually tell us? It tells us that if I take derivative with respect to t of my solution u, evaluated when at time t equals 0, then this is equal to c of x, right? It doesn't mean that the derivative of u it does not mean that if I look at d dt of u of x comma 0, right? Because u of x comma 0 doesn't depend on t, so this would just be 0, right? So you have to be careful about this distinction. Right, and so what does this tell us then? Well, it tells us that c of x is equal to derivative with respect to t of u of xt evaluated when t is equal to 0. But now that I've written this in the correct way, I can again plug in my formula for u from above. So let's do that. So this is now derivative with respect to t of f of x minus ct plus g of x plus ct when t is equal to 0, right? And so now let's just differentiate. Well, in the first term, I have to use the chain rule. I get minus c times f prime. And then the second term, I get c times g prime, right? And while I'm evaluating this when t is equal to 0, right? So this tells me then, in summary, that c of x has to equal negative c times f prime of x, again, setting t equals 0, plus c times g prime of x. And so what am I going to do? Well, I want something just involving like the functions f and g. In this case, their derivatives. So let me just divide by the letter c. Right, so this tells me that minus 1 over c, or let's actually just divide by c, not minus. So 1 over c times c is equal to minus f prime of x plus g prime of x, right? And so this tells me that 1 over c times c, if I just rewrite this, right? And so, right, so let's just pause for a second and collect what we've derived so far, right? So we saw that the function phi is given by the sum of f and g, and the function c, if I at least divide by this constant, is equal to minus f prime plus g prime. Right, and so what we want to do is now piece these two pieces of information together to actually arrive at a solution. In particular, well, notice that the formula for the second line here, the formula for c, involves derivative of f and derivative of g, but the formula for phi does not involve derivatives. And so if I'm going to actually relate these two things together and try to get any new information out of this, I want to differentiate phi. So this tells me that phi prime, right, the first line I can of course differentiate it. And so phi prime is going to be equal to f prime plus g prime. But now I have a formula that looks a lot like the second one, right? Except there's certain terms with opposite signs. And so in particular, notice that in the first formula, I have positive f prime. And in the second formula, I have negative f prime. So that tells me if I add these together, those are going to cancel out and I'll get information about just g, right? And so let's do that. Right? So if I add the first equation to the second, look at phi prime plus 1 over c times psi. This is equal to, well, f prime and minus f prime cancel, and so I just get 2 times g prime. Right. On the other hand, well, instead of just adding them together, I can also subtract them. And so notice if I subtracted these two equations rather than adding them, since the g prime terms have the same coefficients, they're going to cancel out if I subtract, right? So if you look at phi prime minus 1 over c times psi, well, that's going to be f prime minus negative f prime plus g prime minus g prime. And so again, those are going to cancel. And so what do we get in summary? Well, when I added these two equations, I get phi prime plus 1 over c times psi is equal to 2 times g prime. And then the second equation was phi prime minus 1 over c times psi is equal to 2 times f prime. And so now if I just divide by 2, right, so I have, let me just rewrite this if I divide by 2. Right, so now I have formulas involving f prime and g prime, which is what I was kind of involving the functions f and g in some way, which is what I was after. Right. Okay, and so this is a good first step, but remember the solution u is not defined in terms of the derivatives of f and g, right? If I go back to this formula from the last lecture, in order to find u, I need something involving the original function f and the original function g. On the other hand, over here we have something defined in terms of f prime and g prime. So it's not quite what we want, but the good news is that at least we've related f prime to the initial conditions in this way, and we've also related g prime to the initial conditions. So what do you do when you have a formula involving derivatives of functions, but you want information not about the derivatives, but about the original functions? Well, you have to reverse the differentiation, so you need to take antiderivatives, right? So that's what we'll do now. Right, just to get back to f and g. Right, and so let's begin with the equation involving f. If I take an antiderivative of the second equation, we get, oh, sorry, this is not a negative. That was just from the 2 when I erased it. Sorry about that. Right. So if I take an antiderivative of the formula involving f, what do we get? Right. So f of x, take antiderivative. This is going to, if I take antiderivative of 1/2 phi prime, that's just going to give me 1/2 phi of x. And then I'm going to have minus 1 over 2c. Well, what's the antiderivative of c? If I use the fundamental theorem of calculus, I can write this in this way as integral from 0 to x of psi. Since I'm taking antiderivatives, there's also going to be some constant a, which is independent of x. Right? Right, so this is a formula, given what's boxed off in blue, this is a formula, this is what this implies about the function f, right, by taking antiderivatives. On the other hand, I can do the same thing for the formula involving g, right? So now I'm going to have 1/2 times phi of x, now plus 1 over 2c. And then when I take antiderivative of the c term, again, it's going to be integral from 0 to x of that function. And then finally, again, there's going to be some other constant here, which is also independent of x, right? So some number b. And so if you look at what we're trying to prove, this looks a lot like the formula I have here, except in this formula, there's no constants a plus b. right? So we just want to try to understand, well, what happens to these constant terms. One thing to point out is that, well, notice here I have integral of my function c divided by this number in the second formula. In the first formula, I have the same thing, except it's divided with an opposite sign, right? And so once again, this tells you that if you add these two formulas together, some terms are going to cancel out and you'll be able to obtain more information. Right, so if I add these together, well, I get f of x plus g of x is equal to, well, I have 1/2 phi plus 1/2 phi, which is just phi of x. These integral terms cancel out, and then I get plus a plus b. So this tells me that if I add f and g together, I have to get phi plus the sum of these two constants. Well, this should look familiar because before, remember, we showed that phi is already equal to f plus g. But if phi is equal to f plus g, then these constant terms have to add up to 0, right? So this thing has to be 0, since we already learned from before that phi is equal to f plus g, right? And so in particular, well, I don't actually know what a is and I don't know what b is, but I do know that when I add them together, they have to cancel out. So a has to equal minus b. And so this is why these terms will cancel out. Okay, and so now we're basically done. Why are we done? Well, I've written my function f, which is coming from the solution in terms of the initial conditions, and I've also written my function g, which is another piece of the solution in terms of the initial conditions. And so we can just plug in what we know and we'll be done. So, well, we have u of xt is equal to f of x minus ct plus g of x plus ct. And so, right, so what we're going to do is plug in these terms respectively for f and g. Right, so in the first formula for f, I'm going to plug in x minus ct in place of x. And so what do I get then? I get 1/2 phi of x minus ct, and then minus 1/2c times the integral. Again, I'm replacing x by x minus ct times this integral of psi or psi. And then I have this other number a, right? And then I'm going to do the same thing for the formula involving g, but I'm now going to replace x by x plus ct. So I get 1/2 times phi of x plus ct plus 1/2c. And now I'm integrating from 0 to x plus ct of the initial velocity. And then I also have to add on this number b. Right, and so now let's collect like terms. So collect the terms involving phi and then collect the integrals together. Right, and so this tells me that u of xt has to equal, well, I have 1/2 phi of x minus ct plus 1/2 phi of x plus ct. And then, well, I'm adding the two integrals terms together, so I have plus 1/2c times integral from 0 to x plus ct plus, or minus, sorry, 1/2c integral from 0 to x minus ct of the initial velocity. And then I also have these constant terms that add together, right? So plus a plus b. But the good news is that we just saw that these have to cancel out when I add them to 0. And so now we're basically done. We just have to combine, right? So what do we have above in the theorem, right? I had this term involving 1/2 phi of x minus ct plus phi of x plus ct, which we saw below. And then I have this integral term, which is just going to follow by combining the two integrals we have here, right? So I want to combine these using the fact that that you can, right? If you have the integral of the same function over certain intervals, you can combine those, right? So we're gonna do that, right? And so if I finally simplify this, I get 1/2 times phi of x minus ct plus phi of x plus ct. And then, well, I have 1 over 2c integral from 0 to x plus ct of my initial velocity. And then, well, notice if I switch the order of integration, if I flip it over, I get a minus sign. So that's going to become integral from x minus ct to 0 of my initial velocity. And now x minus ct is going to be smaller than x plus ct if t is positive, which is a reasonable thing to assume. And so I can combine these integrals and then I'm done. So this is equal to 1 over 2c. Right, I'm integrating from x minus ct to 0 and then from 0 to x plus ct. So these things combine. Right, and so that's the proof. Right? So that's the formula that was stated above. Right. And so this is how D'Alembert would have derived it originally, right? You're sort of just following. I mean, at each step, we're really doing the only thing we can do with maybe a little bit of being a little clever at certain points. But really, I mean, you know u is a sum of these two functions f and g, and so the natural thing to do is just try to relate by plugging in t equals 0. Relate these functions in the best way you can to the initial conditions, and then you have to do a little bit of algebra and calculus to simplify things and collect terms. And that's basically it. Okay. Right, and so we saw one example of how to like apply this. Right, you're given some function phi and some function c, and you just plug into the formula and you have your solution with those respective initial conditions. I just want to do one more example, which is related to like what we looked at to derive this equation. And so this is usually called the plucked string example, where we have a certain initial condition, which is going to be similar to if you had like a guitar string or violin string and you pick up a point in the middle and then release it. So what does the solution look like in that case? Right, and so what is my, right, so let's try to draw a picture here. And so this axis will be my u-axis and this will be my x-axis. And we're going to suppose that my initial condition is, right, something like that, right? So let's say I pluck the string at a certain point. Say this is equal to, say this is equal to 1, it has height 1, and say this is positive 2 and this is negative 2. And then after this point, my string is just the x-axis, right? So I have a horizontal string and I just pluck it up at a point here. And so let's say this is my initial state, right? So this is my function, the blue line is a graph of my function u when t is equal to 0. So this is my initial position phi. Right, so maybe instead of state, maybe position would have been a better term. And let's suppose that the initial velocity is 0. Right, so this is just at the moment when you've plucked up the string, there's no velocity because you're holding it there and nothing is moving until you release it. Right, and so initial velocity is my function c, and let's say that this is equal to 0. Right. Okay, and well, now we just have to plug in to our formula from above to see how the solution acts. But first we want to find a formula for phi, right? So what does this function look like? Well, notice that if I'm between, right, so it's going to be piecewise defined, right? Because if I'm between -2 and 2, or if the absolute value of x is less than or equal to 2, it looks like some kind of like minus absolute value function. But if x is bigger than 2, it's just 0, right? Right, so I'm not letting the absolute value function extend, right? It's piecewise defined. Right, and so, right, so what does this look like? Well, again, you see this corner point, so you think, okay, it's minus absolute value, although it has a certain slope. So the slope of this is going to be change in y over the change in x. So it's going to be -1/2 absolute value of x. And well, when x is equal to 0, it passes through the point 1, right? when x is equal to 0, the value is 1, so it's going to be 1 minus 1/2 absolute value of x. Right, so this is my function phi. It's a piecewise defined function. And so what is the solution then? Well, u of xt is equal to 1/2 times phi of x plus ct plus 1/2 times phi of x minus ct. And so at each point in time, well, you have to use this formula to actually understand what this looks like, right? So when t is equal to 0, it's just going to look like the picture I drew above. As t evolves, it's going to become a little bit more complicated. Right. So one thing that I want to point out, which is one thing that I want to point out is, well, what happens? Okay, so maybe for short periods of time, what this string looks like is going to be a little involved, because notice that at each different value of t, you have to plug into this formula for phi and see what the solution looks like. But what happens if, like, as t grows, right? So let's say as t gets large, right? So I pluck this string and then I let maybe I let a few seconds pass. Then what does the picture look like? Well, notice that right. So what is, maybe it'll help if I just draw some pictures. So let's say I try to graph the first function, say 1/2 phi of x plus ct. Well, this is just my original graph here, but it's shifted to the left, right? So this looks something like, right? So it looks like the same thing, except it's been shifted a few units over. So this is at minus ct instead of the origin, and maybe the origin is back over here. And so this term has moved to the left. It has half the amplitude, so this is now, the height is now 1/2 instead of 1. On the other hand, if I look at the other term, 1/2 of phi of x minus ct, well, again, it looks a lot like the graph of phi, except maybe it has half the height, but it's been shifted over to the right, right? So it's now at plus ct, so it's moved to the right. And so maybe actually let me combine these pictures, and let's suppose the origin is over here, right? Well, then after a certain point of time, it looks like the solution is completely separating, right? So this plucked string that I've lifted up above here, if I let time pass for a certain amount, then it's going to split into two different pieces. And since I'm adding these together, there's no interaction, right? The domains, when these are non-zero, are now, after enough time has passed, are disjoint. And so this one displacement that you've picked up is going to separate into two different traveling things, which are going in opposite directions and don't interact anymore. So this is kind of what the solution looks like after a large period of time. And so the only way to see this is actually the case is by using D'Alembert's formula, right? Because if I just use this more abstract formula over here involving f and g, I don't know how the functions f and g interact unless I have more information about the initial conditions, right? So this is a particular example of that here. Right, and so if you look in the book, the book goes through this example in a little bit more detail, where it actually has some pictures of what happens in the intermediate cases. Like if say t is very small, what does it look like, and how does it evolve to get to this picture? So I would recommend reading through that example as well. Okay. Okay, and so, right, so we at least at this point know how to, if you give me a certain initial position function and an initial velocity function, I can write down a solution for the wave equation on the whole real line. The next thing we want to talk about, which is material related to section 2.2, are various like mathematical properties and which have physical analogs, physical properties of solutions to this equation, right? And so this is, let me start a new page. Right, so we're looking at 2.2 now. We're going to talk about some properties of solutions to the wave equation. And so the first thing we're going to talk about is something that's usually referred to as the principle of causality. Which is related to the example we just looked at with the plucked string. And so the idea, well, what's the idea here? So let's remember our solution formula, u of xt. And so this is going to be a consequence of this D'Alembert formula, which we derived at the beginning of the lecture, right? And this formula is exactly what I'm copying over now. Right. So let's try to understand what this says about how the solution behaves at a particular point in space and time. So what I'm going to do is I'm going to plot, let's say this is my x-axis, and let's say the vertical axis is now t, right? Just as a warning, right? This is not the same picture I have up here with u in the vertical axis. Now my vertical axis is not measuring displacement, but just time. Right, so this is t-axis, not a u-axis, just to avoid confusion. And let's say I pick a point, say x comma t in space-time and fix it. Right, so we're just looking at some fixed time, point x and point in time. So how does the question we're going to ask is, well, how does the solution u depend on the initial conditions, right? So how does, or the value of u, say value u of xt, depend on values of the initial condition? Right, so physically, like if you know certain information, physical information about the initial position of your wave and the initial velocity, how do these two pieces of information affect the future behavior of the wave, right? This is the type of question we're asking, which is why this is usually referred to as a principle of causality, because we're talking about causality. Okay, well, if I fix my point x and t, how does this value depend on the initial position? It only depends on the initial position at 2 points, right? So say this is x minus ct, and this is x plus ct. Say this is x, right? So this value only depends on the value of phi at x plus ct and the value of phi at x minus ct, right? Because these two, whatever these two numbers are, they determine the first piece of the formula. Well, that's not it. It also depends on the initial velocity, right? But let's just do this one piece at a time. Right, so the initial position phi only contributes to the solution based on these two particular points. And so what about now the initial velocity? Well, this is a little bit more complicated because we have an integral of the initial velocity, which is this function c. But notice that the integral is over a finite region. And in particular, it's the region or the interval that's between these 2 points that I just drew, right? And so it's exactly, I'm integrating on this blue line here, right? So this is the integral from the interval from x minus ct to x plus ct. And so u also depends on the values of the initial velocity in this interval. Right, so values of the initial velocity function c in the interval from x minus ct to x plus ct. But otherwise, it doesn't depend on the initial conditions, right? So out here, like say in these regions that I'm highlighting in red, so the values of the initial position function phi and the initial velocity function c in this red region do not affect the solution. right? So it doesn't matter what's going on at this particular point. It doesn't matter how the functions phi and psi behave in the red region. They have no impact on the value at this particular point. Right. And so one way that this is typically drawn is by, well, notice if I draw a line like this and a line like this, you can calculate that these have slope 1 over c. So this region is typically referred to as like the domain of dependence, I think is the term. Right, right. So this blue region is called the domain of dependence. Right, because it sort of encapsulates the region in, or sort of it encapsulates the extent to which the initial conditions can affect the solution, right? So, right. And so notice that if I picked, let's say I pick another point, in space-time, like say I pick another point, say y, comma s, and let's suppose that, let's suppose y is between x minus ct and x plus ct, meaning y is in this interval, and let's say s is less than t, right? For example, maybe my point would be, like say this is y, maybe my point here, this is my point ys, this is s. Well, if you go back to the original formula, or if you go back to the solution formula, and now I look at, say, plug in y is equal to x and t is equal to s, I have a similar formula, and so now it turns out that, maybe I'll do this with orange, right? So now the value of u at this point, it's only going to depend on y minus ct, and then also maybe y plus ct, and then maybe the integral. So that's where it's going to depend on the values of phi at those 2 points, and then the values of the initial velocity in this interval. And so you're going to be able to draw this triangle here, which is sort of the analog of what I just did. And so notice that this triangle is actually contained in the larger one. And so if you do this for any point with shorter time, or smaller time, like say less than t, you're going to get some triangle that's contained inside this larger triangle. And so this triangle kind of captures all of the past history of what was going on with your solution, right? Because the only relevant information for the value at y comma s is contained in this triangle, if you draw the picture this way. And this triangle is contained in the larger triangle, which encapsulates the relevant information for what happens a little bit of time later. So for this reason, this is sometimes called the past history of u. Right, so it's either referred to as the domain of dependence or the past history. Right. And again, if that was a little complicated, the main point is just the original picture I drew, right? So the main point is that we're looking at the question, how do the initial position and velocity affect the values of the solution? Well, the values of the solution only depend on the value of the initial position at 2 points, if I fix x and t at 2 points, and then on the initial velocity, the integral the values in a particular interval. Okay, and so how is this useful in practice? Right, so I'm going to write this down as a theorem, which is basically going to say the same thing as the picture we just drew. And so I'll call this theorem the principle of causality. This is sometimes called the finite speed of propagation for waves. And so what does it say? Well, suppose my initial position phi of x is equal to 0 if, say, absolute value of x is bigger than a. and suppose that my initial velocity is also equal to 0 if absolute value of x is bigger than some number a, right? And so if I look at this picture, or let's say I graph, like say this is my x-axis, right? Say this is a and this is minus a. Well, this is the region where my initial conditions are not 0. If I look at the red region, so I'm assuming that phi is equal to 0 here and c is equal to 0 here, right? And so this should mean if we go back to the analysis we did up here, you would expect if both of these initial conditions are 0 in these regions, then there should be some related region where my solution u also has to be equal to 0, right? Because for example, let's say there's some, right? I mean, let's say first, for example, that I mean, if both of my functions phi and c were 0 in the blue line I drew up here, well, that would imply that u has to be 0 at xt, right? And so it's the same sort of idea. And so how does this work out? Well, the conclusion is that u of xt has to be equal 0 whenever absolute value of x not bigger than a, but bigger than, say, a plus ct. Right, and so what this says is that, okay, when t is equal to 0, then the domain of u where u is not, the region where u is non-zero, is exactly the region where phi and c are non-zero. And as t evolves, the region where u is not 0 spreads out at speed c. Right, so there's going to be an interval of x where u is not 0, and that's going to increase with time because the wave is going to spread out, but it can only increase at speed c. Right, and where am I getting speed c from? I'm getting, well, this, right? So this tells you that the speed that it's spreading out as t evolves is c. Right. And so one conclusion of this, right? So the wave u of xt cannot move faster than speed c. Right. For example, let's just draw a picture. So now I'm going to use, my vertical axis will be the u-axis or the displacement axis, and this will be the x-axis. Let's suppose my solution looks something like, say this is the graph of phi of x, which is u of x comma 0. Let's say my solution looks something like this. Right, and so maybe this is a over here and this is minus a, and so outside this region, my solution is 0. Well, what this says is that if I let time evolve, well, the wave can spread out and move around, but only at a certain speed, right? So for example, let's say now I let t equal 1. Like what happens if, say, 1 second or 1 minute or whatever your units are evolve? Well, now this interval will increase. Say I have a plus c and a minus c. And so in this region, u can be non-zero. I don't know exactly what it looks like, but outside this region, there's no wave, right? So outside this region, u is 0, right? Right, so it's not going to be the case that, say, at like time t equals 2, there's a point way out at like when x is equal to 1,000,000 or something, 1,000,000 times a, where u is non-zero, right? So the wave is not jumping from the origin to some other point like instantaneously, right? The speed of movement of the wave is restricted by this parameter c. And so this is kind of like a very simplistic version of this principle that nothing can move faster than the speed of light, right? Because like light has an interpretation as a wave, and you can't have like a light wave jump from one end of the universe to another, and it's right. It has to travel at speed c, and this speed limits how the solution behaves. It's this type of idea. Right. Okay, and so I mean this principle of causality, maybe when you actually try to write it out in detail, it looks kind of complicated. But again, it's really just the main thing to keep in mind is just this picture I have here, right below principle of causality, which is just right. If my initial conditions are 0 outside of this region, then u has to be 0 outside of this region. It's that type of thing. Okay, and so I haven't actually proved this, so let's go through the proof. It's going to be pretty simple as basically a consequence of the D'Alembert formula again. Right, and so let's just recall this formula one last time. And so we're assuming that phi of x is 0 if x is bigger than or equal to a, and also the same thing for c. And we want to show that, okay, before I write this, so we want to show that if the absolute value of x is bigger than a plus ct, meaning if I'm sort of too far out of this, what's called this domain of dependence, then u has to be 0. Right. Okay, and so since we have an absolute value of x, we have to break this up into 2 cases. So the first case is when x is positive or bigger than or equal to 0, so that absolute value of x is equal to x. And so in this case, this says that x is bigger than a plus ct. Okay, well let's think about this for a second. If I go back to this D'Alembert formula, the relevant points again from the values of phi and then from also the domain of integration, the relevant region is this interval between x minus ct and x plus ct. Well, let's look at this formula, this inequality I have here. This says that x minus ct is bigger than a, right? And so let's say this is the point a over here. X minus ct is bigger than a. Maybe this is minus a. Well, this is the region here where my phi and my c are non-zero. And so if x minus ct is bigger than a, that means that both of my initial conditions are 0. Right? And so therefore this implies that, well, phi and c are 0. And so if I just look at the formula at these points, I just get u is equal to 0 plus 0. So this implies that u of xt is equal to 0. Okay. And so case 2 is going to be similar. And so now we have to assume, well, what happens if x is less than 0? Then absolute value of x is equal to minus x, which implies from the hypothesis that minus x is bigger than a plus ct. Or if I rearrange this, this tells me that Right, right. Actually, that's probably enough. Sorry. Right, right. Let me rearrange this. So this tells me that minus x minus ct is bigger than a, and then if I multiply it by -1 on both sides, this tells me that x plus ct is less than minus a. Sorry about that. Right, and then so here we have a similar issue, right? Because let's say this is the domain of dependence, or the domain where my initial conditions are not 0. Well, this tells me that x plus ct is outside to the left of this interval. So maybe x plus ct is over here. But then x minus ct is also to the left of that, right? And so this is the region where my solution lies at this particular point. But now phi is 0 here and c is 0 here. And so u is 0 also. Right, it's the same argument as before, just kind of like the reflected version. Right, and so this implies that u of xt is 0 as well. And that's the proof, right? We had to consider separately the cases where x were positive and negative, but assuming that, I mean, now that those two cases have been handled, we've shown exactly what we wanted to show, right? I mean, at the end of the day, this is really just a somewhat more technical way of saying that if I have a solution to the wave equation and with speed c, that the solution u cannot move faster than speed c, and that's what this all says basically. All right. Okay, and so in the final part of the lecture, we're going to be talking about another physical observation which is associated to the wave equation, and so we're going to be talking about the energy of the solution. Right, for various applications in physics, for example, or engineering, you want to understand, well, how do you measure the energy of the system? So we're going to now assume that we have a solution to the wave equation, and we're going to think about, like, how do you calculate the energy of this wave, right? Right, and so for this, we're going to want to recall what this constant c was equal to. So c squared was equal to the coefficient, or the constant of tension of the string divided by the density, right? So T was the tension, rho was the density of the string. And so what does the wave equation say if I plug this in? It says that if I multiply the density of the string times UTT, this is equal to the tension of the string times UXX. So what's the reason I'm reminding everyone about what these constants are? Well, we want to talk about energy, and so a starting point is to look at the kinetic energy. And so the formula for kinetic energy is, recall, 1/2 times the mass of the string times the velocity squared. And so when we talk about the mass, that's going to be related to the density, right? Right, I have some density here, so that's going to be relevant for the mass. Right, and so the first thing we're going to do now is calculate a formula that describes the kinetic energy, and then use that along with what the equation says, to determine what a good equation is that describes the potential energy. And then by adding these two equations together, we get a mathematical formula for the total energy of the wave, or of the system. Right, and so how are we going to plug things in and obtain the kinetic energy? Well, remember that the mass of string, say on a small interval, right? Let's say I have some point xi, and then some point xi plus 1/n, where this is a big number, excuse me, where this is very tiny. Well, this is So the mass is approximately the density, which is rho, times the length of the interval, right? And so then what is the velocity at the point, say, xi, right, the left endpoint of the interval? Well, the velocity is the first time derivative, which is ut at xi and time t squared. And so we would expect that in a small interval of length 1 over n, where n is just some large parameter, we would expect the kinetic energy to be approximately rho times ut at xi evaluated at time t squared times 1 over n. And so then a good approximation for the total kinetic energy, well, it's going to be what you get when you sum up all these intervals over the domain, right? So sum over I of rho times ut of xi n squared times 1 over n, where say xi plus 1 is xi plus 1 over n, right? So I have some partition of my x domain into tiny intervals of length 1 over n, right? And so you should recognize this as a Riemann sum, right? So now we're going to let n go to infinity. Where remember n is the length of these tiny intervals, and as n goes to infinity, since this is a Riemann sum, it's going to converge to the integral of rho times ut squared. Right. And so this is going to be the definition of the kinetic energy for the wave equation for u. Right. Okay, at this point, you may raise some, I mean, if you're paying attention and you're being pedantic, you may raise some issues about this integral, because remember, we're looking at the domain where x is between minus infinity and infinity, right? So this is our domain of integration. So if we come down here, this is an infinite integral. So how do I know that this quantity is finite if I'm not integrating over a finite region? There are a few ways around this problem. For example, you can request that the solution U has sufficient decay as x goes to infinity or minus infinity such that this integral is finite. Another way around this is to refer back to what we talked about right before this, related to the principle of causality or the finite speed of propagation. So suppose there's some really big number r, such that if I'm outside the interval of length from like say minus r to r, that both my initial conditions are 0. Right, so say outside some this, where r is some really big, like bigger than any number you can think of, right? Well then, what does my kinetic energy look like? So kinetic energy, notice I'm integrating my function u, I'm integrating a derivative of u. Well, from the principle of causality, we have u is equal to 0 if x is bigger than r plus ct, or minus x is less than r minus ct, if you go back to the theorem we just proved. And so if u is 0, then the derivative of u is 0 here too. Right, and so this function ut is 0 unless I'm in this range, right? So unless I'm in like say, minus r minus ct to r plus ct, right? So for example, if you assume that your initial conditions are 0 outside some very large but finite interval, then there's no issues with the convergence of the integral and the definition of kinetic energy, because it's always over a finite interval. So for our sake, we'll always be assuming that the initial conditions vanish outside some gigantic but finite bounded interval, and so that there's no issues about the kinetic energy being infinite or something like that. So it's always finite for us. Okay, and so this is just kinetic energy. Of course, you hopefully remember from physics that the total energy is given by not just the kinetic energy, but also by the sum of the kinetic energy with the potential energy of the system. So let me call the total energy, say at time t. Let me call it a function capital E of t. And so this should be equal to the kinetic energy, which we just derived, plus say that I'll call it PE for potential energy. What we want to do is find a formula for the total energy, right? Not just for the kinetic. So we have one piece of this formula, but we need to find out what the other piece ought to be. Right. And so at this point, we're going to use some more input from physics. And so remember, we have the law of conservation of energy. Law of conservation of energy is exactly what it says, right? It says that energy is conserved over time. In particular, if you have if there's no more complicated interactions, you would expect the total energy to be constant in time. Mathematically, what does it mean that the total energy is constant in time? It means that if I look at this function, this energy function, E of t, if I take the derivative with respect to t, there's no change with time, so this should be equal to 0, right? So in calculus terms, law of conservation of energy is just derivative with respect to t of this energy function is 0. Right? And so that tells me then that, well, if I differentiate the equation for the total energy, I should have 0 is equal to d dt of the energy function, which should be equal to time derivative of the kinetic energy plus the potential energy, both of which depend on t, right? And so in particular, the potential energy function, I know at least that if I take the derivative of this with respect to t, this should be equal to the negative of the derivative with respect to t of the kinetic energy function, which was this integral we derived above. And so we're going to use this observation to figure out what the potential energy should be. Right. So the next step is to calculate the time derivative of this formula for the kinetic energy. Notice that this indeed actually depends on t because I'm not integrating with respect to t, so this is some other variable, right? And so for the rest of the lecture, we'll just do some calculus computations. We'll arrive at a formula for the potential energy, and then we'll be done for the day. But the main point, the rest of it, you're just going to see some clever mathematical calculations and some tricks which are useful and you should keep note of. But the main important kind of physical principle we're using here is just the law of conservation of energy plus the definition of what kinetic energy is equal to, right? So these are relatively simple principles we're using as input. So now the complicated part is just doing the math to simplify things. Right. So let's find out what the time derivative of the kinetic energy is. Right, so from the formula above, this is equal to the derivative with respect to t of the integral of rho times the time derivative of u squared. Oh wait, sorry, did I forget excuse me, I left out the 1/2 from all these formulas, right? So I just did mass times velocity squared. So divide rho by 2, right? So it should be 1/2. Sorry about that. Right, so there should be a 1/2 out here. I mean, it's not a big deal, but just to be completely correct, I should be careful to include that. Okay, and so now let's take the derivative with respect to t of this expression. And so this is a calculation which is very similar to something you did on your first homework, right? So we're going to use this trick of differentiating inside the integral. So this is equal to rho over 2 times the integral of the derivative of ut squared with respect to x. And so now to differentiate this, we have to use the chain rule. So this is rho over 2 times integral. The 2 comes down, and then I have 2 times what was inside, which is just ut, and then times the derivative with respect to t of what was inside. So in that case, I get the second derivative with respect to t dx. And so the 2's cancel, right? So that's why you want the 1/2, because it makes these formulas nice and the 2's will cancel out. Okay, and at this point, I'm going to use that u as a solution to the wave equation. So utt times rho is equal to t times uxx, right? As we saw above, since u solves wave equation. And so if I plug this in, I get that this is equal to now the integral of ut of xt times uxx of xt, right? Second derivative with respect to x now. And then I also have this constant, which is related to the tension of the string. Right. And so, right, so a good candidate for the potential energy is the negative of this, right? So therefore, we expect that if I take the derivative with respect to t of whatever the potential energy function is, that this should equal, well, remember we had a minus sign floating around, so this should be minus the tension constant times this integral. And so what I want to do in order to find the potential energy function is try to, right, I would have to take antiderivatives with respect to t. And so what I want to do is write this as derivative with respect to t of something. Because if I can do this, then I can take antiderivatives of both sides to reverse this, and then I'll get a formula for the potential energy. And so if you look at this as it's written, you may not really see a way to do this, right? There's not at this point an obvious way to write this integral on the right-hand side as the time derivative of something. And so if you got to this point, you may now get stuck. And so at this point, it's good to introduce a very helpful kind of principle for dealing with partial differential equations, which is whenever you're stuck in a problem that involves integrals, you should always try to just integrate by parts. So this is a very useful trick, right? Which is when stuck, try to integrate by parts and see what you get. And so this will definitely show up later in the class at various points. And in the future, if you take more classes involving partial differential equations, you should always have this in the back of your head, like you integrate by parts whenever you can to try to see what it leads you to. Right, so what happens if I integrate by parts with respect to x in the above integral? Well, I have minus t times integral. Actually, let me ignore the minus and the t for now. So if I just look at the integral, if I integrate by parts, well, this is like my dv and this is like my u, right? So the derivative will move over, but then I have the boundary terms. And so the boundary terms are ux times ut. The bounds for this, let's say, are minus infinity to infinity. And we're going to assume that these functions sufficiently decay so that this is 0. And then I have the other term, which is negative integral, where I switch the derivative. So now I have du times v, which is utx times ux dx. Right. Right. So this will be 0 since we're assuming decay at infinity, at plus or minus infinity. More precisely, the way to make this work, for example, would be to use this remark, right? So I put after a certain point, as you're taking the limit towards infinity, after a certain point, you're going to hit 0 on both ends. So when you evaluate these boundary terms, they're both going to be 0. And so therefore, well, what do I have? So I have minus t times integral of ut times uxx is equal to positive t times the integral of utx times ux dx. And so now maybe it's a little bit easier to see why this is the derivative, the time derivative of something, right? So remember, we want to write this as, I want this to be d dt of something. Sorry. Right, so I want this to be d dt of something. And so, well, let's look at what we have in the input of the integral. I have utx times ux. Is this the case that this is the derivative with respect to t of some function? Well, notice I have a certain time derivative here, right? So let me call v as ux. So this is time derivative of v times v. And so this is something like v prime times v, if your prime is the time derivative. So this should remind you of taking the derivative of the square of something, right? Because if you take the derivative of the square of something, the power of 2 comes down, you have the derivative of what was inside, and then just times the original function again. And so, right, so vt times v is actually 1/2 times derivative with respect to t of v squared, right? Which you can just see from the chain rule. And so if I plug this in here, well, this is now the time derivative of just ux squared times 1/2, right? And so therefore, after all these calculations, I get minus t capital, or minus the tension times integral of ut uxx is equal to derivative with respect to t, or let me not skip that step. So equal to the tension times integral of derivative with respect to t of 1/2 ux squared dx. And then I can bring the derivative outside of the integral. So this is derivative with respect to t of the tension constant over 2 times ux squared dx. And so from above, we had the expectation that derivative with respect to t of potential energy should be equal to the right-hand side. And so now we're exactly in the position we wanted, right? So I have derivative with respect to t on both sides of the equation. So if I take antiderivatives, on the right-hand side, I get 1/2 times the tension times integral of ux squared. For completeness, let me plug in the, right? So it's u of xt squared dx. And so that's my formula for potential energy. Right. Okay, and so then to conclude, we have the formula for total energy, which is E of t. So it's given by the kinetic energy, which we saw was rho over 2 times the integral of let me remind myself, it should just be ut squared, right? And then we had, right, so this is the kinetic energy, which is that term, plus the potential energy, which is the second term. So the second term was now the tension constant over 2 sorry, that should be ux, times the x derivative of u squared. Right? And so this is our formula for energy. However, there's actually a little bit more that we can say, right? Because recall that if I take the derivative of energy with respect to t, this should be 0. Right? Because of the law of conservation of energy. And so what does this say? This says that E of t is constant in t. And therefore, whatever this energy is, I mean, it looks like a complicated integral to evaluate. It's always equal to the same thing when t is equal to 0, right? Since it's constant, let's plug in a nice value, which is, for example, t equals 0. It has to be equal to that number. And so therefore, the energy is equal to integral of rho over 2 I of ut of x comma 0 squared plus t over 2 times ux of x0 squared dx, right? And so, well, I can at least evaluate some of this in terms of my initial conditions. So the first term here, this is just the initial velocity. So this is c of x squared. And then I have this other term here, which is like the initial derivative with respect to x, which is maybe more complicated. But this is another formula for your energy. Okay, and so I guess that's it for today. So just as a quick recap, right? We derived this D'Alembert formula. We proved that it works. We looked at some examples, and then we discussed this principle of causality, which is really just the fact that waves have to move at finite speed. So the values of your solution can like jump around all over the place. And then we also discussed how to mathematically describe the energy of a solution to the wave equation. So the next lecture, we're going to start talking about the diffusion equation, and we're going to see that the theory of the diffusion equation and actually understanding solutions is a lot more involved than in the case of the wave equation. So it's going to take us a little more time. And also, for example, which is maybe kind of surprising, we're going to see that things like the principle of causality will fail for the diffusion equation, meaning it's possible for solutions to the diffusion equation to essentially travel at infinite speed. Which is maybe counterintuitive, and one of the reasons why we spent some time going into detail about this phenomenon for the wave equation, because it turns out to actually be quite rare for the sort of things we're looking at in this class. Right, so that's it.